Good evening everyone, I am Mikas, register number 24BC1656 and this is my DA3 documentation for computer networks. The title of my work is Network Throughput Analysis under Varying Traffic Conditions using Wireshark. In this work, I selected throughput as the network parameter for analysis. Throughput is the amount of data successfully transmitted over a communication channel in a given period of time, usually measured in bits per second. It is an important practical parameter because it reflects the actual useful transfer achieved using under real traffic conditions. In this study, throughput was analyzed under four different traffic conditions: normal, low, medium, and high traffic. The aim was to observe how increasing control traffic affects throughput levels, fluctuation, and stability. The objectives of this work were to analyze throughput under varying traffic conditions, compare throughput across normal, low, medium, and high traffic, study how increasing traffic intensity affects network behavior, and generate multiple graphs for technical interpretation. This DA was initiated by referring to Sharpest's resources and Wireshark documentation related to traffic analysis and throughput visualization. Wireshark documentation helped in understanding traffic capture and packet analysis, while Scapy documentation supported the pro, programmatic processing of the saved packet capture files. Architecture. The architecture of this work consists of four stages. First, controlled traffic was generated using HPeng3. Second, packets were captured using Wireshark. Third, the saved capture files were processed using Scapy in Python. Finally, Matplotlib library was used to generate throughput graphs, which were then analyzed and inserted into the blog. The work was carried out step by step using Wireshark, HPeng3, Scapy, and Python. First, the correct active interface and local gateway were identified in the WSL environment. A baseline capture was recorded under normal traffic. Then low, medium, and high traffic were generated in a controlled manner using HPeng3 by changing packet interval and packet count. Separate captures were saved for all four conditions, and those capture files were later processed in Python to generate the throughput graphs. For the normal traffic condition, Wireshark was started and a baseline capture was recorded without additional artificial load. For low, medium, and high traffic, HPeng3 was used to generate controlled traffic. The packet interval and packet count were adjusted so that the traffic intensity increased gradually from one level to next. I will now briefly show the working environment and the command used for packet generation and graph generation. Here I am showing the working directory that contains the saved packet capture files, the Python script, and the generated graphs folder. I will now demonstrate the low traffic packet generation command used in the experiment. This command sends controlled SYN packets to the local gateway using a defined interval and packet count. Similar commands with lower intervals and higher counts were used for medium and high traffic generation. Now I will show the graph generation step using the Scapy based Python script. This script processes the saved capture files using Scapy and generates the final throughput graphs. This confirms that the 20 graph files were produced for the analysis. I will now show the 20 graphs included in the blog. I will explain the main groups of graphs and highlight the most important observations. Graphs 1 to 4 show the main throughput curves for normal, low, medium and high traffic. These are the most important baseline graphs in the analysis. From these graphs, it is clear that throughput increases as traffic intensity moves from normal to high. At the same time, the fluctuation and the irregularity of the curves also become more visible, especially in the high traffic condition. Graphs 5 to 8 are zoomed versions of the four traffic conditions. These are useful for observing short interval behavior more clearly. The zoom graphs show that low traffic remains controlled, medium traffic becomes more active, and high traffic produces denser short-term fluctuations. Graphs 9 to 12 are smoother throughput trend graphs for the four conditions. These remove short-term noise and make the overall traffic pattern easier to interpret. They confirm that the average throughput level increases from normal to high traffic and the heavier traffic conditions remain elevated over time. Graphs 13 to 15 are summary comparison graphs. Graph 13 compares the average throughput, graph 14 compares peak throughput, and graph 15 compares throughput distribution across conditions. These graphs makes it easier to compare the overall behavior of the four traffic levels in a compact way. Graph 16 to 20. Graph 16 to 20 provides higher level analytical views of throughput. These include overlay comparison, normalized comparison, cumulative transferred bits, histogram of throughput values, and throughput variation using standard deviation. These graphs are useful because they show not only throughput level but also pattern similarity, total traffic volume, value distribution, and stability. From all 20 graphs, the overall result is clear. Throughput increases as the traffic load increases, but the network behavior also becomes more irregular and less stable. This means that heavier traffic increases transmission activity, but it also increases fluctuation and reduces predictability. The main findings of this work are that throughput rises with traffic intensity, heavier traffic introduces stronger fluctuation, and different graph types reveal different aspects of the same parameter. Time series graphs show spikes, smoother graphs show broader trends, cumulative graphs show total data carried, and comparison graphs show overall progression clearly. Possible recommendations are that throughput should be monitored together with traffic variation rather than only with average values. Controlled traffic generation should be preferred for reproducible studies, and future work can combine throughput with delay, jitter, and packet loss for deeper analysis. AI tools were used to support documentation, structuring, code drafting for Scapy-based analysis, graph title refinement, and technical interface writing. However, the actual packet capture, command execution, traffic generation, and graph generation were carried out as part of the real experiment workflow. To conclude, this DA successfully analyzed network throughput under normal, low, medium, and high traffic conditions using Wireshark, HPing3, Scapy, and Python. The results show that as traffic load increases, throughput also increases, but the traffic pattern becomes more irregular and less stable. This demonstrates that throughput is an effective network parameter for studying controlled traffic behavior and practical network performance. This is my This is my GitHub repository which contains the Python script, graph files, and supporting material used in this work. Thank you everyone.